Well, good morning. What you're going to see here is the result of a 2-year study that I did about gunshot residue and how the angle affects that. My hypothesis was that angled gunshots will produce less gunshot residue than orthogonal shots. And the angled gunshots will also affect the size, shape, density of the GSR pattern. Now, gunshot residue, I'm going through the basics here. I'm sure most of you people, and really all your people here are familiar with this, but I started with the basics. Gunshot residue, what is it? It's particulates. I'm interested in the particulates that come out of the muzzle when a gun is fired. Unburned, burned, and partially burned gunpowder. The standard distance is performed with the same firearm and ammunition with bracketing distances until the test pattern that you get in a test matches the actual pattern of the clothing or the body or the wall or whatever the substrate was that was struck. The distance determination method is based on the conical spread of gunshot residue. And there's a diminishing quantity of gunshot residue as the particles move away from the muzzle. There's diminishing density of gunshot residue, and there's increasing diameter of the gunshot residue pattern. Now, this is a little animation, just gives a display of the theoretical distribution of the gunshot residue particles. Here you'll see a high-speed video of the gunshot residue. Here's a bullet coming out, and there's this is the gas ball. There's the bullet, and the particles precede the bullet for a while, and then accompany the bullet, and then follow the bullet. So you'll see a stream of particles that are still coming out of the muzzle. Now, the distance determination method uses diameter and density. With contact distance, you'll get a shot that is very focal. There'll be all the gunshot residue will be in one area. As the distance increases, there's a spread of particles. And as it increases the distance 2, the second distance, and the third distance, and finally at a certain distance, you'll get no gunshot residue. So the distance determination method that we've all used, that we've all been educated in, I found that the foundational document for this is in the old AFTE journal in 1990 by one of the great firearms examiners, an AFTE member, John Dillon, who worked at the FBI lab. And he defined it as a comparison of residues found on a shooting victim's garment with those found on test targets fired at known distances using a suspect weapon and ammunition can have a great deal of significance in court. And it certainly can. And the references for this, all the references, I looked up all the references for shooting distance determination, and they always describe it as orthogonal. I'm going the wrong way here. Let's see. All the testing is described as shooting orthogonal, which means perpendicular to the target. But I wanted to know what if the actual angle was not orthogonal? What if you have a shot that goes at a great angle here, acute angle into the body like this? And reviewing things, there's many shootings that occur where the angle is not orthogonal. So is it proper to use an orthogonal or perpendicular test to determine the distance when the actual shooting was at an angle? So that's what prompted me to start this project. So my research methodology was to shoot what I call 0 degrees, which is this way, perpendicular or orthogonally. And then at 30 degrees, 45 degrees, and 60 degrees, I shot 3 times with each angle. And I did 12 shots per series, a total of 36 shots. I used 2 types of ammunition, 45 ball, all from the same box, flattened ball powder. I used a 5-inch barrel Kimber, and then I used a 9mm Blazer, also flattened ball powder with a Glock. And by the way, the flattened ball powder, I didn't select that powder. That's what it happened to be when I decided to take a look at what powder I'm actually using. The directions of, first of all, I used the targets were either bench coat, which I think you're all familiar with, or 100% cotton twill fabric sheets, and they were stapled to 1/4-inch cardboard. And all my shots were either orthogonal, that is 0 degrees, or from left to right as you're looking at the target. My experimental setup was I had a tripod here at a particular mark the distance, so the distance is the same for every shot, and then I carefully measure the angle that this presents relative to the gun muzzle for each shot. All targets were then photographed, and even lighting is essential because I found this out the hard way. I have many challenges putting this together, because when you're dealing with fabric, what I started with, I started getting a lot of false positive results, and I'll explain where they came from. But it's because of the weave. The fabric has weave in it. And in the interlocking fibers, in the interlocking weave, there are little shadows. And the shadow can be interpreted by image analysis software as a particle when it's not. Now, the targets I had to photograph with, I went through all sorts of methods for photographing the targets because they had to be evenly illuminated. And I also considered putting them on a scanner, which you would think that'd be a great way to do it, put them on a scanner, a flatbed scanner. But I didn't want to affect the GSR that was on the targets. I didn't want to rub them off or make them fall off or leave them behind for the next target. So I had to have everything face up. So I used this type of thing. You can't quite tell. There's 3 concentric LED ring illuminators. And the camera's up here, you can't see, it's in the dark. So I use a completely dark room, no light in the room. The camera's in manual mode, so there's no changes in the exposure, shutter speed, or anything. Same settings for all the targets, and I include a negative control, a target that has not been shot, blank target. Now, my goal was to analyze each target for the quantity, size, and location of the particulates. But I got into this problem, how do I count these particles? You know, you got all these little particles here. How do you count them? What's an effective method for counting them? And I came up with all sorts of ideas. First, I thought I was going to I'll take a representative sample for certain areas. But even that, you know, you're going to start counting 1, 2, 3, 4, 5, 6. It just is not an accurate way of counting particles. So what I found was that there's an image analysis software, which is open source, which means it's free, it's openly available. It's used by many scientific organizations. It's called Fiji ImageJ. ImageJ, Fiji is sort of the version of it. And that will, it was developed by the National Institute of Health and Laboratory for Optical and Computational Instrumentation. It's used very widely in biological sciences for counting cells, anything that's small objects. It can count individual cells. It can distinguish the cells from the background. So This software allowed me to count the particles. It'll count every little particle. It will measure the dimensions of every particle. It will locate the particles on the target. And then with this data, I can perform statistical analyses. So the image analysis procedure is get the target, photograph them, load these photographs now into image J, and then I use the negative control as first to eliminate false positives. You know, I give it a target that's not been shot, has nothing on it, and it should come up as a zero particulate count. Then I know it's correct. The settings are correct. Then I identify the rectangular area of interest, and then the only manual thing you have to do with this program is identify the bullet hole and mark it out, just outline it so the software knows that's not a big particle, that is the actual bullet hole. So it excludes that. So then it has an intensity-based segmentation routine. Now, if there's nothing else you come away from in my talk, I've got a bunch of other interesting things, I think. But this is the meat of it. This is what it's all about. Okay, if I start out with 100% particle count, orthogonal, shooting 0 degrees, and as the angle increases, the amount of GSR particles decreases substantially, almost 80% at 60 degrees. So there's a whole lot less GSR at 60 than there is at 0, and so on. You can read the the numbers right there. So this is the most important part of it, but there's more to it. The density, you know, you look at the density of the particles, and the density, it also, of course, density is just the particles over the square centimeter, and they follow the same relationship as does the quantity. So there's a lot, the density of the particles is much lower at an angle. You know, even a 30-degree angle, you have 20% less density. I tried to do a linear regression. My co-author, Dr. Marco, is a statistical expert, a PhD scientist, and he's also an expert in image analysis using image J. So he did that work for me. And I asked him, I said, can we do a linear regression? Well, we tried to, but it didn't work out. But it did come out very well for whatever reason, where we have a sigmoidal relationship with this shape. And I have sort of a theory why that is the case. And this is on the bench coat targets. And then when you look at the fabric targets, they're similar. And we got very good, I'm going to go back one. We got very good agreement, the validity with the R squared value. So the GSR particulates, and when you compare the bench coat and the fabric, there's a difference. There's a difference in the amount of particulate that's retained. Now, what's interesting is that here, as the angle increases, look at the big change here from 30 to 45 degrees. And I think this is because there's a dynamic that's associated with the critical angle. We all know the critical angle in bullets, ricocheting or not ricocheting. There's a certain angle at which they will ricochet and a certain angle at which they'll penetrate. And I think that's also what's happening with the gunshot residue particles, that at a certain angle they will bounce off, and at a certain angle they wouldn't. Now, we also looked at the dispersion of particles by looking at the Euclidean distance between the particles. And that we found the dispersion, you know, the density is the amount of particles per particular area. Dispersion is the distance between different particles. And the mean dispersion of the particles varies quite a bit, as you can see. This is a 45 degree, and by the way, I used two different distances, 7 inches, 18 centimeters, and I used 15 inches, 38 centimeters. And you can see how the dispersion in this goes up quite a bit. And I don't know why, but it just, there's the data. Maybe someone here can figure out why. The distribution of the particles is mostly on the left side, which makes sense because all the targets were shot left to right. And there's the distribution and the size of the particles you can see at different angles by these generated shapes. And of course, you can see as the angle increases, the shape becomes more and more ovoid. The 60 degree is a lot more ovoid than the 30, for example. All shots, you can see here, put together. This is the 0 degrees, and as the angle increases, you get more ovoid shape. So the ovoid shape is important. It's an important concept to remember, to be aware of, because if you're going to test an object for gunshot residue, like a shirt, for example, you may want to test, I suggest, if you don't know what the angle was, test a wider area than just the center area. Because I've seen this done where just the center, like a 5-inch diameter area is tested. Well, there may be gunshot residue elsewhere on that target. And you may not see, it may not be visible to you, to the naked eye, but it certainly should be tested. Now here's a case where they used this filter paper, I think it was 6 inches in diameter, but they failed to test the rest of the garment, where if it's an angled shot, you'll have this ovoid distribution, and all the particles will not be in the center. So how do you know if it was an angled shot? Now, in this one case I had where a sweatshirt was sent to the lab, very good examiner there, and they said, tell us, here's a gun, here's the ammunition, here's the shirt, tell us what angle this was, or tell us what distance this was shot at. So he did a standard test, orthogonal, boom, 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 and he made a determination. And they never told him there was a very steep angle, very acute angle in there. So when he was asked, well, did you know that the angle was quite acute? He said, nobody told me. And I think this is now it's like a sanctified state that you're supposed to be in, where you're not supposed to know anything. You just determine things out of pure science. And I don't think that's helpful. I don't think that's really scientific to start out that way. So how do you know what the angle is in the shooting? You may not know. Someone maybe can tell you, or you can look at the shape of the hole. That'll often tell you. If you have a hole like this, the bullet wipe is a very good indication. Here's a 45-degree impact into like a blue denim. And you can say, well, look, that's not an orthogonal shot, so you might want to incorporate that in your testing. The bullet wipe is a very good indicator if you have it, even more than the shape, because the shape can be kind of ragged, the actual shape of the fabric, but the bullet wipe is very nicely defined. So here 0 degrees and here 45 degrees. So back to the research project. So my question came up, okay, we have less particles, we have 100% of the particles at 0 degrees or perpendicular, and then we have 21% at 60 degrees. Well, where do these other particles go? What happens to them? So I set up a little hypothesis that these particles bounce off, skid off. The bullet goes like that. Most of the particles hit the target here at a particular distance, and some skid or bounce off. So I wanted to test this sub-hypothesis. First of all, here's a video where I shot into cardboard. There it goes. Okay, here you see, there's the bullet, and there are the particles coming. And look at these particles here. Look at them skidding off. So another test I did here on fabric, where you can see, it's hard to see here, but here are the particles, and you see them climbing up here. So to test this, to see where these particles go and how much of the particles will skid off, I created this little test with an adhesive sheet. I put this adhesive sheet perpendicular to the plane of the target. It's a sticky sheet. It's, it's one of these peel-off boards that you're going to mount something on or stick it to a wall or whatever. So I put a piece up there to capture any particles that would be skidding. So I'm shooting like this, thinking that the particles will be caught and retained in the adhesive sheet. So this is a setup I did at 30 degrees and 60 degrees, with the red indicating the sticky sheet. So this is what I found. The two targets compared, 30 degrees and 60 degrees. As the angle increased, there's more particles are found on the sticky sheet, which kind of makes sense. I mean, that's where they go. They do skid and ricochet off the target. So then I had a question, how many GSR particles can you expect? Well, it's going to vary with the type of ammunition, the type of powder, and I think many other variables. But so I showed that at an angle, some particles will ricochet off, but I wonder how many particles from an orthogonal shot will just bounce off the target. That is, if you shoot directly at a target orthogonally, 0 degrees, will all the particles stick to the target? So I shot a bench coat target at 0 degrees, and then a sticky target, an adhesive target at 0 degrees. And I found that normally, the sticky target, you have 2,250 particles. On the bench coat target, you have 950 particles. So more than 50% of the particles are not retained. And what I also would suggest that you keep in mind is that the different substrates have different retention properties. And I found that with the bench coat and the cotton fabric, they all have different retention properties, that the GSR will stick to them or not, depending on the type of material and whatever the dynamics are involved in that. So my hypothesis, back to the original hypothesis, I believe is confirmed. With angled shots, the GSR particle quantity is diminished. The particle density is diminished. The particle dispersion is increased. And the pattern diameter is altered. The angled shots will alter the pattern diameter. Pattern shape is altered. Implications. In distance determination tests, actual angles should be replicated. If you know the angle, a proper distance test will incorporate that angle, will replicate the angle. There's no, using orthogonal testing for distance determination did not come down from the mountain. That's the way it started, but now we have to, I think about the actual dynamics of the incident. And I also think it's important, when possible, I think the standard is to use a cotton twill fabric. Well, that fabric may not retain GSR as well as whatever the actual garment was, or the wall, or whatever the other substance was. So actual shot dynamics should be considered. An awareness that the absence of particles may not be from the distance alone. And back to John Dillon, one of the great men of AFTE, he wrote this in his protocol, where he says the absence of gunshot residue is not a basis for expressing a distance determination. Prior to issuing conclusions, the examiner should understand that shooting events are dynamic and they must consider the possibility of intervening objects or other limitations when determining a maximum distance. Well, what I'm saying is other limitations. Well, the angle is another limitation. So that's it. That's the whole story. Any questions?
When it comes to looking at the angled shots on the bullet wipe, I'd be very careful in interpreting that, because in most cases that I've encountered, the clothing isn't on a human being like it is mounted on a piece of cardboard. So all of the natural folds and bends in the fabric could alter that shape of that bullet wipe. So I'd be cautious to try to interpret the angle just by the bullet wipe.
That's a very good point, and a very valid point. That clothing doesn't always fit skin tight, and you have folds and rumples and so on. So the angle at which the bullet struck the fabric may not actually represent the angle at which the gun was fired into the body. Next.
So within our agency, we've been trained that when you observe kind of that oval-shaped pattern, so you know an angle is involved, use the narrowest diameter you can, as that is more likely to be representative. I'm curious, have you done or could you do, since you have images of the full pattern, effectively crop it down to a narrow stripe in the middle in order to compare those using the image analysis to see if that practice is applicable? Do you, if you narrow down to the center stripe, would you have an effective, consistent density between your different angles? Or should we be careful doing that, because, as you've shown in the ricochet, it might lead to decreased density throughout?
I don't know the answer to that, because I've never looked at that particular protocol, that method of using a strip. So I don't know, but I think that it's much better than using a circular measurement.
Good job, Alec. Well presented and understandable. I would even urge all of us, if it's very critical, if we're getting down to issues about could he hold the gun or is it beyond the reach of a person, and the final analysis, tell the agency, I'm going to shoot some of the actual jacket. Your jacket, for example, if it had a pattern in the front, I'm going to cut out, ultimately after the bench coat or the jean twill, I'm going to cut out a section of that coat and try to refine it. And that will help. I think that will be helpful in when it comes to cross-examination.
Yeah, I think that's absolutely true. I think you should test with the same material. If there's a bullet hole in this jacket, use a portion of the jacket that's not going to be affected to do your distance determination test, because you'll get the retention of the particles can be expected to be the same as the entry hole. And I've done a lot of cases with clothing, and all the clothing, when they have a little tag here that says the manufacturer's name and the size and whatever, there's often, or I think always, an RN number, RN, the long number, and my understanding is that that's the fabric number, and if you can match that fabric number, that RN number, now I may be wrong about this, maybe I shouldn't tell you this, now that I'm thinking about it. I hope that, I didn't really research that, it just came to mind, but I've used that before to find the fabric with the same RN number. So if there are no other questions, well, thank you very much. Thank you.
Quick observation.
Didn't see it.
I think when representing the angles, it's probably more appropriate to represent the angle between the target and the trajectory of the bullet, rather than between the target and the normal. So maybe in fitting your data, you might get a bit of an easier way of interpreting it if you just swap those angles around.
I didn't understand, I'm sorry. The
So
swap,
instead of saying the first one being 30 degrees, the first one would be 60, and then the 60 would be 30 because of the angle between the target and the trajectory of the bullet. That, if you think about taking a circle on a 90 degree, you could transform that circle into the elliptical shape, such as in bloodstain, by adapting that angle. Because it's that angle that's going to describe the shape of the ellipse.
So are you saying to use that type of analysis to determine the angle?
Well, there's
The major and minor
I'm just
axes?
saying when you're measuring, for instance, in the 30 degree, the angle between the target and the bullet trajectory is actually going to be 60, as opposed to 30 to the normal surface.
Oh, well, it depends how where you're measuring, from where 0 is.
Well, yes, and it's going to be the
Yeah,
reciprocal.
so what's
of
the
that.
difference?
Well, you can transform a circular pattern from 0 degrees to 60 degrees, and it's going to match the pattern of your oval, your elliptical shape of your dispersion pattern, and which one of the previous speakers was talking about. We're going to be reducing perhaps in the x direction, but the y distance is going to stay constant.
Okay, I hadn't thought about that. Thank you. Anything else? Okay, thank you. Thank you.